Okay, so this graph, you kind of have to interpret what this graph is. So you're running two different situations. One at 90 degrees, one at 70 degrees.
April Fools.
That's funny. So, what this is representing, and you have to understand what the axes are. So this is the collision energy. So this is how much energy these particles have when they run into each other. Don't worry about the units, it's just a scale. So this could be like, 5, 10, 15, 20. It doesn't make any difference. As you go across, the collisions have more and more energy. So this is the number of collisions that occur at a particular energy. Now, one.
Her pencil was fire.
So one of the things that you need to understand about temperature is that you got to get out of this mindset that we say, oh, hey, you measure the temperature of water. And you look on the thermometer and it says it's 35 degrees, okay? That 35 degrees is the average amount of kinetic energy that the particles have. So this is important. You have to understand what's going to happen today. That when we talk about temperature, we're talking about the kinetic energy of the particle. For those of you that haven't had physics, kinetic energy is the energy of motion. It comes from the Greek word kinesis, which means motion. So when you say the water is at 35 degrees Celsius, that doesn't mean that every molecule of water has the exact same amount of energy. Some might have more, some might have less. But we're saying on average, as a species, we have said that if you look at those old school thermometers and we say, okay, when this amount of energy is in there, that level goes up to a certain point. We made a mark on the glass and we said, that's 35. Okay, there's nothing magic about it. We just said, that's 35. But what's important is that that is not the true measure of every particle that's in there. Just like if I said the average height of students at Mays High School is 5 foot 5 inches. That doesn't mean everybody is 5'5". Some are going to be less, some are going to be more. On average, it's 5 foot 5. So when you say the temperature is a given value, that means that also within that, there's some variation within it. Now, so this line over here is what we need to talk about today, is the activation energy. The activation energy is the threshold energy that has to be overcome for a reaction to take place. So if you think of this in terms of second graders, so the activation energy is the height of the bar that the kids have to jump over to as part of their recess. So along comes Timmy, okay? Timmy has to run along, go, oop, jump over the bar, okay? So the activation energy is the height of the bar that the kids have to jump over in terms of a chemical reaction, because atoms, molecules, whatever, actually don't want to be near each other because they all have this electron cloud that's around them. So there's a certain repulsive force but that has to be overcome. So for example, you all have generated hydrogen gas. Oh, let's drop in a piece of magnesium and in hydrochloric acid, and you see bubbles of hydrogen gas form. So actually, if you think about that, here's this one proton, and it has that one chihuahua running around it. Here's another proton. It has another. So something has to overcome that repulsive force between the two hydrogen atoms, and Mother Nature goes, I'm going to gain something from it. So the only way hydrogen bonds together is if that repulsive force of the electron clouds, whatever comes afterwards, is at a lower energy level than the two hydrogen atoms separately. Okay, so what this says is that at 70 degrees, so let's start with the top line. At 70 degrees, we're saying a lot of these collisions, not all of them, but a lot of them are at this collision around this 5 to 10 range. You have some that are a lot less. You have some that are a lot more. But at that 70-degree mark, and here's this activation energy, there's only a small number of those collisions that are above that threshold. Now, this is why I had you do the lab yesterday, because so now this chart makes more sense. When you guys ran it at that cold temperature, what happened to the rate? Decreased. Became very, very slow, right? Why?
They're not as excited.
Now, here's what I want you to think through. Listen to me very carefully before you answer this question. Which had the higher activation energy?
He wants us to take Chem.
No, you didn't. If you did, you thought incorrect. What had the lower activation energy? The cold temperature, the warm temperature, or was the activation energy the same? The activation energy was the same. Okay, I never changed the activation energy. Just like here's the height of the bar that the kids have to jump over. I don't change the height of the bar. But what happened at cold temperatures, you had a much smaller number of those collisions that were above that threshold. So that's why it took so much longer. Eventually, all the reactions did take place, but the percentage of collisions above that activation energy were much smaller. Now, you run that at 90 degrees. A lot more as a percentage of those collisions are above that threshold. That's why on that warm, when you warmed it up to like 40 degrees, some of you got done in like 15, 20 seconds. Because of the fact that we didn't change the activation energy, we just made a lot more collisions that occurred above that. So, if in terms of second graders, you have two situations. One where the kids are outside and it's like 30 degrees Fahrenheit. And we're going to make the kids jump over the bar. And it's like, kids, we're not going inside until everybody jumps over the bar. Okay? Now, at 30 degrees, because it's cold, not a lot of kids initially are going to be able to jump over the bar because it's cold. Okay? They will, but it's going to take a long time. Now, in contrast to that, you do the same thing, but it's 80 degrees outside. Okay? We're not going to change the height of the bar, but at 80 degrees, a lot more of those kids have that energy. It's like, oh, great, I can do this. Yeah, watch me. Boom, jumped over. Look, I got a puppy. Watch me jump. Okay? So a lot more of those kids, as a percentage, are going to be able to jump over that bar. Now, you can do the same thing. Let me ask you this. I'm going to set out 2 bowls of water. Okay? Same amount of water is in both bowls. One bowl of water is at 10 degrees Celsius. One water is going to be at 60 degrees Celsius. Which bowl will evaporate faster? Why?
Because it's going to take less energy to turn into gas.
It's close. I'm going to say kind of neither, because 60 degrees is like room temperature.
It's Celsius.
I don't know about that. This is in Celsius. 10 degrees is not room temperature.
Bro, 60 Celsius.
What, Big Mike?
Are we talking about which bowl would like evaporate first?
Yes.
The only thing different is the different temperatures.
Yes.
Oh dear.
The 60 one. The 60.
I agree, Big Mike.
Because it's hotter.
Why?
Isn't it harder to
Because
boil?
because
It's easier to boil cold.
I'm not boiling it. This is just evaporating.
Wait, you're not
This
boiling
is
it?
just evaporating. I'm not boiling it.
Wait, but that's,
I'm just going to watch it evaporate. Water evaporates.
Well-
That's why you swim, right? You get out of the water. What happens eventually?
You know, I actually don't know.
You never got out of the water?
Yeah, no.
wait, we can't see it happen. So how do we know it evaporates?
Okay? So the 60-degree water is going to evaporate faster because they have more energy to break the bonds and hold the water molecules together. Okay? So there's a certain threshold of energy that you have to cross to break the bonds and hold the water molecules together. Okay. So here's the point. Activation energy. Threshold. You have to cross over. Higher temperature, more collisions happen above that point. Now, if the activation energy is out here, what would happen?
Nothing.
Nothing. because none of the collisions would be above that point. So if you got that solution cold enough, you could sit there all day and nothing would happen because of the fact that none of the collisions were above that activation energy. So that would be like having second graders, and you're going to set the bar way up here. No matter, it's not going to happen, okay? Because of the fact that Timmy is not going to be able to jump above that bar. Okay, got that idea. Another one. Same idea. This is as the reaction proceeds. And this is energy. Okay. So let me explain what this graph is. So you can visualize this. Let me grab an oxygen. Is that, let's say that we want to have the reaction between hydrogen and oxygen. Okay? So, which seems relatively simple, but it's actually fairly complex. So, we want to blow up hydrogen and oxygen. So I go get the balloon filled with hydrogen gas. It reacts with oxygen, and we produce water. Two. So this is how things exist. You have the hydrogen gas, like this is the molecular form, and then you have the molecular form of the oxygen. So at some point, I've got to break these bonds. So I've got to break the bonds that hold the oxygen atoms together. Because otherwise, if I don't break these bonds that hold these together, I can't make water. Because I have to have just one oxygen. So I've got to break these bonds that hold these together. Okay, I've got to break those bonds. That took a certain input of energy, this activation energy. Then I've got to break the bonds that hold the hydrogen atoms together. I got these pulled apart like this. So the top of that hill, right, this activation energy, this is where this is existing as hydrogen atoms and oxygen atoms, okay, because I have to break those bonds. So that activation energy is what goes into breaking those bonds. Now, you're at the top of the roller coaster. That took an input of energy. To get the roller coaster to the top of the hill, that takes energy. It's not going to do this on its own. You have to put energy into it. Then, if you think of this as being like the chihuahuas. So the chihuahuas are in this roller coaster, and they're sitting at the top of the hill. And the roller coaster is going to go down the hill. Now, you all, when we set off a hydrogen balloon, especially those of you that were close enough, you felt the heat from that. Okay? Right? It got warm. So that's like the chihuahuas, they're excited. They're going, woo! Guys, they're going down there, they're going, woo! Okay? So that woo, what you feel, is the energy being released in the formation of the water. So you're at the top of the hill, you're at the transition state. So this would be the amount of energy that the hydrogen and oxygen have as individual molecules. We throw the energy into it, that activation energy, it gets into that transition state, it comes back down now, and then we make water. So in this situation, this is the classic example of what we call an exothermic reaction. So exothermic reactions is when the products have less energy than the reactants. You go down the hill. It's cold in the wintertime. You start the fireplace. Why?
Because it's cold outside.
Well, what's the purpose of starting the fireplace?
To warm you up.
Okay, so is that reaction endothermic or exothermic?
Exo.
It's exothermic. You're giving off energy. You as living beings, you are one big collection of chemicals. Okay?
We're endothermic and we eat.
If you were endothermic, you would be continuously drawing energy from the outside.
Oh, my bad.
Yeah, you're right.
Hey, we're actually cold.
Overall, your reactions are exothermic. Okay? So the sum total of all the reactions that take place in your body is exothermic. This is why you radiate heat. If we were endothermic overall reactions, we would actually be drawing energy in from the environment instead of radiating energy out.
Yeah, my bad. I thought about it like you too.
No.
That's my bad. Something else.
That's almost biology. Stop there. So this is option number one. You have the hydrogen and the oxygen. You break the bonds, you separate them out. At the end, you're going to make water, and the water ends up with less energy. So in this situation, that value is a negative delta E. So what might happen, just to give you some idea of numbers, so that might be, say, at 20 kilojoules per mole, however much energy that is. So down here, that might end up at 15 kilojoules per mole. So it's final minus initial. So if you take 15 minus 20, you get negative 5. So that means that negative delta E is what's energy that is given off. Now, the activation energy is the height of the hill. So let's say that you end up down here at 15, and let's say that activation energy has a value of 30 kilojoules per mole. So what that means is that you're starting off here at 20. You have to pump in 10 kilojoules of energy to the top of the hill. And then from here, it's going to roll down, so you end up at 15. So you're going from 20 to 30, 30 all the way down to 15. So the net change is going to be negative 5. Cool. An exothermic reaction, you feel the heat, boom, there you go. But, and you all have done this reaction as well. Let's say we want to reverse this. Let's say that I give you a beaker of water, and I ask you to separate it into hydrogen and oxygen. You all have done this. What did you have to separate water into hydrogen and oxygen? What did I have to give you to do this? We just did it in the lab in redox. No, close. It rhymes with battery.
Battery.
I gave you a battery. Why? It's non-spontaneous. You had to put energy into this. So, here's the story. If you reverse the process and start here with water, now the activation energy is this big spike up the hill. So my activation energy in the reverse would be the 5 kilojoules here plus that additional one. So the activation energy to reverse it would be a really big number. So one of the ideas to wean us off of a carbon-based fuel source is to use hydrogen fuel cells, okay? And hydrogen fuel cells aren't new. Hydrogen fuel cells is what we used on the Apollo missions to the moon 40 some odd years ago. By the way, in case you're a space junkie, yeah, 5:45 this afternoon, they're supposed to launch the latest and most recent one on the Artemis mission to the moon. So if you're a space junkie, pay attention to that. And so one of the things they can use is a hydrogen fuel cell. And you can also do this in cars. The idea being is that you take hydrogen and oxygen and you combine it together and you just get water. But here's the problem. Even though hydrogen is the most abundant element in the universe, on Earth we have very, 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 very small amount of like free hydrogen gas. We've got to take the water, like this, and we have to break it apart. Well, to break it apart, what does that require? Energy. So the question is, like, where do you get the energy? So here's the problem with this, is that if you reverse this process, now it's like pushing a roller coaster back up the hill. You got to put a lot of energy into this situation. You've got to really push it a long way up the hill. So that becomes the question is like, well, if you've got to burn coal or natural gas to generate the electricity to split the hydrogen from the oxygen, there's no net gain. So this is why you can get what they call green hydrogen production, where they use solar, they use wind, they use something like that to use a non-fossil fuel-based energy to separate the hydrogen and the oxygen from the water.
Why don't we just go to the sun and gather them?
No. Okay,
And if it's too hot, just go ahead.
just a little. All right, so here's what I want you to see. If you reverse the process, the activation energy goes from the bottom to the top. In the forward reaction, that first hill is the activation energy. So, the other option that can happen, and this doesn't happen as often, but we'll study this later. You could also have a situation where you have some activation energy, but you actually so here's still your activation energy. So that might be at 20 kilojoules. And this is energy. And this is the reaction. Now, in this situation, that might be 30 kilojoules. And that might be 25. Now, with this one, you still have this activation energy to put into it. But now, here's what's taking place. Your products actually end up with more energy than the reactants. So in that situation, this is an endothermic reaction. So to do this, you had to take energy in from the surroundings. So with that situation, that delta E would be a positive 5 kilojoules per mole. So that energy has to come from somewhere. So this is why when some reactions, they don't happen very often, and later on you'll see this, Mother Nature likes a hot mess. Mother Nature likes exothermic reactions that increase the amount of disorder in the system. Mother Nature likes fireworks, okay? She likes to sit back and go, ooh, ah, okay? There's a whole other lecture we'll get into later. But I'm just planting to see. Mother Nature likes a hot mess. In this situation, Mother Nature really doesn't like this situation because of the fact that the products end up with more energy than the reactants have. So this would be an endothermic reaction. But here, if you reverse it, the advantage of this is the activation energy becomes less. So if it's an exothermic reaction, and you go to push it back up the hill, your activation energy is bigger than in the forward reaction. But if it's an endothermic reaction, the activation energy is less than what it is in the forward direction. Okay? But it's all about the energy. Okay. Let me see. Now, so this is something that San asked about. Son, I'm sorry.
Very boring.
Let's go back to reading the manual.
No, I can't go. I can't go past. I already checked my time. There's so many pictures out. I'm thinking it's pretty Send your mouth.
Okay, so this is going to get more complicated. So the overall reaction is A turns into C. Okay, it's just a generic reaction. A is going to turn into C. But this is like a camel, okay? And you got two humps, right? Kind of fitting for Wednesday that I give this lecture on Wednesday. So this is it's a camel, okay? It's hump day. And this is a two hump day, okay? Okay. So here's the story. If you've never seen that commercial before. So you have a certain amount of activation energy. So here's my question. Is B a transition state or an intermediary?
Transition.
I said intermediate because like at a certain point the slope is 0.
Oh, just a bit outside.
That is true.
In the middle.
Okay? Never thought of it that way. So the humps are the transition states. Okay? So if you think of this in terms of the ball toss, okay? So here you are, and imagine that I catch it up there at the top when it's in that transition. Okay, so the transition is at the top of that toss. The activation energy is how high I throw it up. Do I go like this? Do I go like that? Okay, so that's how high I have to throw it to get up over a certain point. So that transition state is going to be up there. So then we're going to form B, which is going to be an intermediate. Then I'm going to have a second activation energy here. And then I'm going to end up with out here at a product of C. So let's start with this. Is the overall reaction endothermic or exothermic? Exothermic, why, Shannon?
The energy at the end is less than the energy.
Yeah, it's not much. I'm going to give, so this is a little bit less. C is a little bit lower than it is when I started today. So overall, the reaction, I'm going to have a negative delta E overall. Now, in this situation, my substeps are going to be A turning into B, because I'm going to have one intermediate step. And then B is going to turn into C. So I'm going to form B, but then I'm going to consume it later on. So here's my question. Based upon this energy diagram, what's the slow step? The formation of A to B or the formation of B to C?
How many answers? Don't do this. Let's not sit here.
Trick question.
No, it's not a trick question.
What's the x-axis? Is it time?
It's just the progress of the reaction.
Everyone's in the right one.
Just based upon this diagram.
I'd say A to
What's the slow step? A to B, B to C.
I gotta leave.
Okay. So the slow step is going to be the transition from A to B. Why? That's the biggest activation energy. That's the biggest hill that you have to climb. That's going to be the slowest number of collisions, the lowest number of collisions that are above that threshold. So A to B would be your slow step. So based upon that, since this is the slow step and B is getting consumed, the rate law should only be based upon the production of so your rate law based upon that would just be K times concentration of A, because that's what's going to limit how fast something can be consumed. Okay. Now, these are random equations. I'll explain what they are. Do not memorize them. I will always give them to you if you need them on the test. This gets real complicated, so bear with me.
Are you saying you won't memorize
It's the Arrhenius equation.
Yes, it's the Arrhenius equation.
That's what I
I'm
was
not
saying.
A. I'll leave there.
The Arrhenius equation?
It's pretty.
It's very ugly.
It's pretty elementary, right? Yeah.
You can say that.
That's frequency factor. That's not G's.
That is the A to the power.
Yes. No, it's E to that power.
I did not say frequency. Oh, you're.
Okay. So, are you leaving now? Okay.
This is, well, I calculated how I'm not going to be early for 4th hour, and this is how I'm not going to be late for 4th.
Okay, give me 1 second. I still
Okay.
need to give you sign. So, this is the Arrhenius equation. Let me explain. It's not tough, but then you would have to be given a lot to use this. So A is what's called the frequency factor. That's the number of collisions that are favorable for a reaction to take place. E sub A is your activation energy. Now, this is all about units. This R is your physics R, so that's 8.314 joules per mole Kelvin. So this activation energy has to be in joules. Okay? The temperature has to be in Kelvin. A is what we call the frequency factor. Okay, it's just a number. So what this is, all this is a different way of finding the rate constant. So instead of basing it upon a graph, if you know this information, you can come up with it. Which from this you can derive the equation that we use, which was the natural log of k equals negative. It's just an assignment out of the book.
Oh.
So I just got to write it down on there. So,
I'll take a picture.
okay, there you go. All right.